So, in the first class of high resolution electron microscopy, I have discussed to you the basic fundamentals of high resolution electron microscopy, and we are going to continue from the class where we ended in the last class. So, as I shown you that the contrast transfer function, which is known as the transfer function in a high resolution electron microscope, is basically a very complex function, and it can be written like the one I showed you. Transfer function is equal to 2 where the first factor is as a function of z is basically the aperture function, and this actually is a strong function of the g, and psi is basically the angular factor which comes into play. So, from this function we have seen that how the psi actually plays a very important role, and finally we derive the optimum values of the psi. The one which I can write like this is depends on defocus as well as it depends on the CS, or the aberration, spherical aberration constant, so therefore, the factors which control the constant transfer function basically are the defocus and the spherical aberration constant of a microscope. Obviously, lambda goes into the picture because lambda is the wavelength of the electron beam, and g is the spatial frequency which is inverse of lambda, and so therefore, defocus and the spherical aberration constant demarcates the values of psi, and psi can be as a function of g as we have discussed here, square related to defocus and the fourth power for the CS. So, we know that for a particular microscope CS is a constant, CS values never changes for a particular microscope, but obviously it can vary from microscope to microscope. Also it can be changed if we change the objective length of a microscope. So, knowing that CS is fixed for a particular microscope, the free parameter which can play the important role is the delta f or the defocus, and that is where we actually shown you how this can be determined using different values of CS and different values of defocus, how this function can change. So, we discuss this factor in detail and find out what is the optimum focus limit for high resolution microscopy. So, this is the slide where I am showing you the actual or ideal transfer function when the microscope lenses are perfect. As you see that the no microscope is basically a perfect one, because there will be lens defects like spherical aberration and other factors, astigmatism, and as well as this chromatic aberration. So, chromatic aberrations is very difficult to correct, and because of the aspects that the beams which are falling on the sample may have different energies, but astigmatism can be 100% corrected. On the other hand, the spherical aberration, which is an important factor going into this equation, is very difficult to correct, but of late it has been found that spherical aberration constant can be easily corrected in the electron microscope and can be used. So, this is the ideal spherical aberration, the transfer function which is shown here. So, obviously in ideal transfer functions, as a function of g, the value of 0 in the transfer function should be as small number as possible. The number of zeros here is this, and this is for an ideal microscope, which is not possible to achieve at any cost. So, in a real microscope, the transfer function, so the actual here I am showing you the ideal transfer function for any transmission electron microscope. So, you can see that the transfer function varies, starts from 0, it goes down, and finally, it is basically a square function reaching 0 again at certain value of g, which is at g1. And so, as you know that more 0 means more less number of information going into the going to the from the sample to the image. So, that is why the ideal transfer function will have only one 0 here, and all this information which are here are basically at a low spatial frequency are transferred to the image from the sample. So, which is this kind of situation is never really achieved, because all these microscopes will have defects, and the defects change this transfer function drastically. And I am showing you one such picture where the actual transfer function is shown as Tg as a function of g here, and Tg values can actually can be varying from +2 to -2, but what you can see is that there are a lot of variation, not only the number of zeros have increased in these transfer function, but also the spatial frequencies, depending on spatial frequencies, the values are changing. So, there are higher order values, there are lower order values of the transfer functions. Now, one can actually see the effect of transfer function, effect of the spherical aberration constant on this transfer function. This is what is shown here, which I have shown in the last class itself. If I change the spherical aberration constant Cs from 1 to 3 millimeter, the transfer function changes drastically. For 1, basically the transfer function has a very large width before the first 0 comes here, and again as the Cs increases, this 0 is slowly moving to the left side, the lower value of g, and therefore less number of lesser spatial frequency can be transferred in the actual microscope, and this is done at a fixed value of defocus minus 60 nanometers. So, once we optimize the Cs value, okay, here it is seen that optimization Cs value is basically 1, and then we can look at what happens basically as a function of the defocus, as a function of delta f. So, delta f is varied here for 200 kilovolt microscope with Cs 1 millimeter from -30 nanometers to -70 nanometers. As we vary from -30 to -70, the profile or the transfer function profile as a function of g is changing drastically. For very low value of delta f, that is -30, the g1 comes at a frequency like this, and there are several zeros here after this g1. And as you go from -30 to -50, the g1 value shifts to the right side, therefore more informations for the lower spectral frequency ranges can be transferred to the image plane. But as we increase the value delta f to say -70 nanometers, you can see that g1 actually never reaches the 0 value or 0 axis value, and g2 rather sorry, g1 actually is coming at a higher value, but g2 is another kind of spikes come into picture, which is giving or restricting the transfer function to a much lower value of g, which can be transferred to the actual image. So, these are the two effects of Cs and delta f. Then for a given microscope where Cs values are known, how do I optimize the delta f values? And this is basically done by a scientist called Otto Scherzer in 1949, and that is what we will do. So, as you can understand that the presence of zeros in the what's called in these transfer functions are basically tells you the gaps in the output signal, correct, because these zeros means they are giving no output signal as far as the transfer of the actual things in the sample to the image plane is concerned. So, that means these frequencies can be thought of filter out. So, obviously base transfer function will be 1, in which there are least number of zeros. The one I have shown you one slide back here is basically the ideal transfer function where there are only 1 0, there is only 1 0. So, therefore, best one will be the one where there will be least number of zeros in the transfer function, so that the best resolution is possible. So, in what Scherzer has done, Otto Scherzer long back in 1949, he has basically described the optimization of the focus or defocus in a particular microscope. What is said that the transfer function can be optimized by balancing the effect of spherical aberration against a particular value of defocus. So, that means if I I need to get a particular value of defocus where the effect of CS can be balanced. This delta f is known as Serger defocus, which is given by this formula minus 1.2 CS lambda to the power half. And many times we write this equation as minus 1.2 SCZ, where SCZ is known as given the Serger defocus CS lambda to the power half. So, what you can see clearly from this picture is that the Serger focus is basically tells us that all the beams will have at the defocus, all the beams will have nearly constant phase out to this first 0 or first crossover in the 0 g axis. That is what is shown here. This is the first crossover at the 0 defocus or 0 g axis. So, therefore, all these beams, all the electron beams will be nearly constant phase out to this, and this is what basically required to obtain the best possible resolution or information in electron microscopes. This performance, the best performance obviously will be expected from a microscope at values, first value or first crossover value on the 0 of the g axis, unless and until obviously we do lot of image processing later on, that is we improve the contrast by doing some other means. But this is what is obtained from a particular machine with a given value of CS. Now, how does this formula arrive? That can be basically done by using simply several aspects. So, what you can see from this picture is that from this what's called from the slide is that the closest we can get to the ideal curve which I have shown you is basically corresponding to sigma, corresponding to this value, the xi z to the equal to minus 120 degrees, and that corresponds to sin xi z to be equal to minus 1. So, that means this is the obviously maximum value or whatever minimum value of sin possible, because sin is a bounded function between 0 and 1 or minus 1 and 1 basically depends on the angle. So, minus 1 is the minimum value of the 6 sin is possible, and this is the gives you the best optimal possible the value of transfer function. Now, let us see how this can be basically derived using this formulae which I have already given you for psi. And for psi we have seen that the psi is given depends on the defocus and also the spherical aberration constant. So, this is equal to pi delta f g to the power square lambda g to the power square plus half of pi cs lambda q g to the power 4. So, if I basically minimize this function at a particular value of g, I can get basically the Serger focus. So, let us do that. If I minimize this, I get very simple equation twice pi delta f lambda g plus again twice pi cs lambda q g to the power q, and this obviously has to be 0. So, we can write down this as this plus cs lambda square g square. So, that can be easily seen. So, when psi will be minus 120, so we can obtain from this equation that this is minus 2 pi by 3 equal to pi delta f lambda g square plus half of pi cs lambda q g to the power 4, and combining these two equations one can obviously obtain a simple mass simplified expression of Serger focus or the focus, that is f ch s ch is equal to minus 4 by 3 Cs lambda to the power minus Cs 4 by 3 Cs lambda to the power 1 by half. So, that becomes 1.155 Cs lambda to the power half. So, that can be easily derived by this way, just by putting the derivative, first derivative of psi with respect to z to be 0 for a particular value of psi, that is 120 degrees, because at 120 sin psi is equal to minus 1. So, by using these equations we can derive that Sedgwick optimum Sedgwick focus become 1.155 Cs lambda to the power half, which is very close to 1.2, and this by fine tuning this calculation, obviously one can arrive at the same Sedgwick focus, and which is basically nothing but that balancing act which you do of Cs by putting the focus value at a particular number. And this is routinely done in a microscope nowadays, where the optimum image is obtained at a particular value of Sedgwick focus. Now, obviously one can go ahead and even go to the next step, that is the first crossover is by this, the next crossover can also be calculated, and next crossover as it basically comes at a particular g value. The next crossover can come at a particular g value given by this is 1.51 Cs minus 1 by 4 lambda minus 3 by 4. Okay. And this crossover is very important in the sense that at this defocus, at the basically Sedgwick defocus, which corresponding to this value of g will give us the resolution limit of the microscopes, and these resolution limits can be obtained by taking inverse of this, which is equal to 0.66 Cs lambda q to the power 1 by 4. So, this gives us the optimum resolution limit or the actual resolution limit for any thermal electron microscopes. So, by knowing this number Cs of the objective length and lambda, we can basically get that. That is why you understand now why people use million volt electron microscopes, because lambda can be exceedingly reduced by using higher and higher accelerating voltage from 100 to 200, 300, people have gone up to 1.5, 1500 actually kilovolts. So, by and obviously another way of improving resolution is by correcting the Cs, which you are going to see today in the end of the lecture how we can do that. So, this actually puts us the limits of resolution, but this is not the limits of the information. Information limit is much actually higher value than the resolution limits in microscopes. Okay, information much lower value than the resolution of the microscope. Information can be achieved even much lower. In fact, there are reports that 1970s a detail of 0.66 Armstrong was actually done or achieved, and when the interpreted resolution was about 3.3 Armstrong. So, you can see that actually it details an image does not mean that you can gain any useful informations about the microstructure. So, there is a distinct difference between the resolution limit and the information limits as far as the microscope is concerned. Well, so therefore, these two functions, one is R Sedgwick, another one is the delta f Sedgwick, which is equal to 1.2 Cs lambda to the power half. These two are the master equations in the high resolution electron microscopy. They actually give us the limits for any uses in the high resolution electron microscope, and this was due to Otto Sedgwick, and other one, the first equation is basically developed by Glaser. So, therefore, and these two people, these two scientists are called the pioneers of high resolution electron microscopy for developing this concept in the high resolution electron microscopes. So, that actually sets the tone of the high resolution electron microscopes. So, if many students or many users have misconception that high resolution electron microscopy means just getting a lattice fringe or just getting some information on the computer screen or on the imaging screen where you can see the atomic planes. Okay, but that is not the case. There are a lot of many interesting aspects one is to know. Now, as we have discussed here, or we have shown you that in the transfer functions we normally do not take any of the things which are beyond this first 0, something which is basically coming beyond this number or beyond this G1 value, okay, which is basically of no use to us. But why it is so, or whether this is really true or not, that is what gives us the new concept called envelope damping functions. So, plots on this T g or say psi g, whatever, psi g is also related to T g, psi g versus g, as you can see here, can they be extended from this first 0 to the other values? That is the question we need to ask ourselves, because as you understand, if we can extend this value to the higher g numbers, and g is basically spectral frequency, therefore, we may be able to achieve much better information in the real space, because g is in the reciprocal space. So, if g higher value of g means lower value of x or y or z, the real space variables. So, if we can extend this g to the higher values and include them into transfer functions in an electron microscope, we will be able to achieve much higher resolution and much higher information limits also can be achieved. So, if that is the case, is it possible? Answer is no. We do not use this higher crossover, or we do not extend the values of the g beyond this first crossover normally. Why? This is mainly because of the damping effects, because of the other issues like this spatial coherency of the electron beams and also chromatic aberrations. So, which normally comes into play when spherical aberration is corrected, and these are basically due to spatial coherency, means as the electrons falls on the sample, or basically if you look at the electron beam, how small it, wherever it is, even if it is 1 nanometer or 0.5 nanometer, whether the spatial coherency of the electron beam exists or not is very difficult to ensure even using the fake guns. So, because of this resolution is hampered, or because of these higher the g values can never be accessed. Second one is the chromatic aberrations. Although we can use FEGs or the field emission guns to reduce the beam energy spread to even very low values, still it is very difficult to get 0 chromatic aberrations, or it is actually not yet possible to correct the chromatic aberration to that level. So, because of presence of both this chromatic aberration and the spatial coherency problems, this kind of these frequencies can never be actually used to get information from the sample. Now, obviously, the exactly mathematically this can be derived, and mathematical envelope or form of this envelope functions is very complex, and one can actually simply write the T effective function as a function of g equal to T g E c E a. E c is basically due to chromatic aberration, and E a is due to spatial coherence of electron beam. And once you put this envelope function into the transfer functions, they are coming as a multipliers, as you can clearly see, and this basically gives us limitation of using these higher values of g into the transfer function. This effectively means the envelope function is basically acting as a virtual aperture in the back focal plane of the objective lens, regardless is whatever the value of the defocus. That is what is the actual meaning of that. So, that means physically if we at all put an aperture in the what's called in the back focal plane to remove this unwanted noise, this must be less than size or let the virtual aperture present because of this envelope functions. So, that is why presence of this virtual aperture means higher order pass bands higher order passband means these passbands higher order values are never accessible. It cannot be accessible because of presence of these envelopes. That's why I say that this is nothing but envelope damping functions, or these envelopes are actually these functions frequencies getting damped out because of presence of the envelopes due to chromatic aberration and the spherical coherency. And this is what can be shown there. So, as you see here, this is the sin psi as a function of g. So, there are many such higher order frequencies or higher order d values which gets damped out because of the presence of these envelopes due to EC and EA. So, effect of EC and EA is to damp out this higher order frequency. So, we cannot access them. So, whatever may be the situation, as you can clearly see that there are all the zeros more than higher than the G1, but this beyond that the values of the Tg is very small, and whether this can actually affect the resolution or the information on the microscope needs to be analyzed, and it has been seen that it can affect. So, therefore, although resolution limits will be given by the first crossover, the information limits can be higher. Information limit can be given by this point G2, which is at a higher frequency, higher spatial frequency. So, that is why in many microscopic images, high resolution microscopic images nowadays, whatever you see, all the resolution is about say 0.8 Armstrong for the Titan microscope or 0.5 Armstrong for the chromatic aberrated microscopes, but information can be actually picometer levels. So, we can achieve informations much higher resolution levels or much higher better values than the resolution level given in the microscopes. That is what is possible in the microscope because of this the presence of the small higher order G values in the transfer functions. So, these all give us some extra informations. Now, by knowing all these aspects, how actually in a real microscopist change or operate the microscopes, because as you see defocus has a very strong role to play in getting the actual high resolution images, because delta f what you have seen is a very important aspects, and we have to go to the Serger defocus limit to obtain the best resolution image. So, how do I achieve the delta f Serger in a real microscope? That can be done in many ways. Obviously, first thing one can do is that for example, worst case of constant transfer function is that when the transfer is minimized, that is you just start defocusing the objective lens in such a way that you do not see any contrast on the screen or on the computer screen or on the basically fluorescent skin. So, if you do not see that, that becomes your best. From that you start actually changing the focus value and reach the Serger defocus value. So, this minimum value here, as you can see, is corresponding to this number of sin psi, and this number of sin psi happens to be 0.3. So, therefore, minimum contrast for the objective length focus length is given by minus 0.44 CS lambda to the power half. This can be calculated obviously in an actual microscope knowing the lambda and the CS, but in real microscopic sense you do not need to do. You can simply change the objective focus in such a way that you do not see on the screen anything. That becomes the minimum contrast in the microscope, and from there you start changing the focal length, and as you change the focal length of the objective microscope, you should be able to reach the Serger focus. Otherwise, what can people do is that in some special cases transfer function actually special setting of transfer function are also used. One such is basically aspect is to use something known as pass band, or use larger window in the transfer function, okay, so that we can allow this higher spatial frequencies to contribute to the image. How it is done? Obviously, as you see from this figure, clearly from the next figure which I am showing here, from this figure very clearly you can see is that this requires that psi to be constant. Obviously, psi means this value of psi is depending on the G and also obviously depends on the Cs and delta F. This requires psi to be constant and also d psi to be constant and d psi dg to be very small. One such example is shown here for silicon. As you can see, the sign size varying from -1 to +1 as a function of g here. G is the spatial frequency, and what you can see is that many pass bands, and if I select a pass band which corresponds to the 111 reflection of silicon, what you can see is that I can clearly get to see that psi remains almost constant for this, from this part to this part of G, and d psi by dg is also very small. That means it is not 0, but it is very small value. So, because this side there is also very small and psi is remaining constant, so that we can use these higher order passing bands, and normally this kind of higher order passing bands occur periodically, and one can actually obtain such equation like this, delta F P n to be equal to 8 n plus 3 divided by 2 Cs lambda whole half. So, when n equal to 0, that becomes the first this value here. Okay. So, and that becomes nothing but 3 by 2 Cs to the power half, 3 by 2 is 1.5, and if you take root of that, that becomes 1.15. So, that is because that becomes actually the same as Sager focus for n equal to 0. So, this technique gives you the access to the higher spatial frequencies. Here you can see here higher spatial frequencies, thus the finer details in the real space. As I said, higher value of G means finer details in the real space, and this price is basically is that only price we pay is that now there are many zeros, 1, 2, 1, 2, 3, 4, 5 extra zeros other than the first 0. So, because of this more number of zeros and zeros corresponding to no output signal, and therefore, there will be transfer the more zeros means lower spatial frequencies will give you at more zeros a less information transfer. A transfer function will be heavily affected. That is the only problem, but this is used widely to basically select the focus in high resolution electron images in many microscopes. So, therefore, in a nutshell, I could say that in the lecture for last lecture and this lecture, I have given you very what's called brief picture of the transfer function, how the transfer function actually varies as a function of delta F, Cs, and obviously the spatial frequency G, and how we can use it in different ways to obtain the optimum focus values array or by balancing the Cs. And these all are done routinely nowadays by computer. Okay, so, we do not need to do yourselves. Many times what people many of the users do is that they instead of trying to obtain the optimum Sager focus, we take through focus images, that is we take images at different level of focus, and then we see which is the optimum focus or which is the basically correspond to Sager focus. That can be easily done routinely nowadays using these the digital cameras, where we do not need to spend money to grab image, just like earlier days we used to spend the what's called camera plates, where each camera plate used to cost about hundreds rupees. So, in a normal imaging technique where you use the digital imaging process, you do not rather actually need to spend money for more images or less images you take. So, that is why nowadays one can easily take 3 focus images, where at least 20 images as a function of focus can be taken, and then from there one can actually decide which is the optimum focus image. But that is actually a trial and error method which normally people use, but for the beginners actually this is the best method possible. In fact, when I started using HRTM, I also did the same way, taken through focus images from the almost thin films and then find out which is the optimum focus. Well, that is basically the state of art till 1999 or 2000. From there, a lot of changes happened in electron microscopy, high resolution microscopy. Especially people have started correcting the Cs. As you have seen, Cs plays a major role in deciding the resolution as well also the focus. So, if we can able to correct the CS, then obviously we can get better resolution, better the information in the high resolution electron images, and that is what has been done by a scientist called H. Rose in 1990. He proposed that it is possible to correct the CS value in an electron microscope, okay, by using a set of spherical lenses and hexapoles. And this was a major discovery in the field of electron microscopy. As we know, in a normal camera, we can basically correct the spherical aberrations by using a set of lenses, okay. By basically diverging converging lens type, we can basically do this changeover. So, in a nutshell, this is what I would like to tell you about high resolution microscopy, and I have basically started from a normal camera and how the transfer function can change in electron microscopes, what are the factors controlling the transfer function, and how to actually optimize them. Now, as I have shown you several lectures, several slides actually in the last lecture and in the today's lecture also, that CS, the spherical aberration constant, plays a very important role in deciding the resolution of the transmission electron microscopes. Rather, to break the resolution limit of the transmission electron microscope requires the CS to be corrected. And this started in 1990 by the classic paper published by H. Rose from in optic. As you know that in a normal camera, we can correct the spherical aberration by putting a set of converging diverging lens. Now, in an electron microscope, this can be done by using set of spherical and hexapoles. That is what is shown in the slide. So, as you can see, this is the standard objective lens, this one, the standard objective lens, and the electron beams from there passes through a set of spherical lens and hexapole lens, and by this, when it passes through all this, actually hexapole lens do not affect the paraxial path of the rays, okay, but it corrects the aberration. In fact, it has been reported that it is possible to actually have spherical aberration constant negative, and by getting that, one can actually break the resolution barrier of 1 angstrom, and this is what has been done later on by many scientists, okay, and by Professor Knut Urban and others in the Hans Ruska Center of Electron Microscopy in Germany. They have been successful in making such a corrector possible, and by putting correctors below the orbital lens and above the orbital lens, where both of the what's called probe and the image correctors can be inserted, and such insertion of the correctors leads to tremendous change of resolution. So, as you can see, the CS is corrected, the resolution of the microscope will be dependent on only on the chromatic aberration. So, therefore, resolution is basically can be written as, when CS is corrected, is like this, delta E by E and lambda CC, this is the chromatic aberration to the power half. So, when CS is corrected and delta A E is basically 0.3 eV in a 200 kilovolt microscope, and we can clearly see DCS will be approximately 0.8 angstrom. In fact, if CC is corrected or the chromatic aberration is corrected, which is going on now in the TEAM project in US, it is possible to reach, when CC is corrected also DCS and CC, it is possible to reach 0.28 angstrom. So, you can imagine that by using all kind of correctors, we can actually reach a limit of 0.3, approximately 0.3 angstrom, which is very close to the smallest atomic size. The atomic diameter of carbon atom is 0.899 angstrom. So, atomic diameter of hydrogen atom is 0.5 angstrom. So, we will be able to reach a resolution limit of less than the size of an hydrogen atom. That is a dream which is one needs to cherish, but obviously such a dream will come at a very high cost. Maybe once I know that a CS character microscope cost about several $1 million, actually about $10 to $12 million. So, once CS and CC characters both are actually inserted in a time electron microscope, length of the microscope will be 3-story building, and such a microscope, operating such a microscope requires help of computers. Without computers, one cannot actually operate such a microscope. Well, this is all are getting done, and in fact, CS character microscopes are now available in India. IIT Kanpur is also going to get a CS character microscope very soon, IIT Madras, and many other places like TIFR, Mumbai, and the JNCSR. Bangalore has also got CS character microscopes, and soon there will be many users using the CS character microscopes. And maybe in future in India, we will have CC character microscopes where we will be able to break the resolution barrier to 0.3 Angstrom. Then we can see whatever we want to see, whether atoms of any sizes can be easily imaged. And as I have shown you that in the lot of lectures in the first class, that if we have aberration CS character, here the image shows the change. As you can see, if we correct CS, we can clearly see the dumbbells, silicon dumbbells. So, that means we can clearly achieve the resolution of 0.8 Angstrom, which is sub Angstrom resolution, and from 0.8 to 0.3 will take us to a different domain of world or picture. So, by using simply CS character microscope, as I shown you in the first lecture on HRTM, even we can image the oxygen atoms in the strontium titanate. It has been reported by Jia et al. In Science 2003, and now it is a routine things. People can actually image oxygen, nitrogen, carbon atoms even, which are very small, using because resolution limits are reached. That is value 0.8 is very easy to achieve. Now, I do not want to go into all kinds of numbers, but let me show you how even 1970s people used to do electron microscopy and get high resolution microscope. This is taken from the Van Dyck et al. Of the group of Amelings and the Van Tendalu in Belgium long back. It is done in 1992, even before the characters have come into picture. This is the 8 dark field image of AU4Mn. What you can see here, all the black and white dots of atoms, which you do not know which one is what, but you can see the antiphase domain boundaries marked by these white circles. Also, you can see lot of distortions, huge number of distortion in the picture. Next one is taken from a set of pictures by many authors, some of us is our. So, we can actually image gain boundary of germanium. You can clearly see it consisting of the dislocations at different intervals. Each one has one dislocations, low angle gain boundary consisting of parallel set of dislocations. You can see that gain boundary of Si3 and 4 silicon nitride has amorphous layer on the very small thickness, about say 0.5 Angstrom, 0.5 nanometers, sorry, and then phase boundaries between NiO, Al2O4 nickel aluminide, which is spinel, is very flat and very sharp. Last one, D, is basically profile image all along 0001 surface of hematite, where you can see the black and white dots of iron. This was used to be the case in 1990s till 1990s, but advent of CS character microscope has made a lot of changes, and it was possible now to pinpoint which atom is what, and to the resolution of the level less than Angstrom. So, therefore, basically this all nice and fine, you can easily routinely get this in CS character microscopes, but the real problem comes how to interpret the images, or how to really get the information from the images. That is where the real challenge, as I said, the real handicap of high resolution microscopy is to interpret the images. Our interpretation of images requires simulations. Simulation needs a lot of a priori knowledge as per the crystal structure of the material is concerned, atomic positions are concerned, also interaction of the electrons with the sample, how this interaction is dynamic, as we have seen. So, in the next class I will just describe some of the simulation techniques, and then I will move on to much advanced techniques like STEM, or scanning transmission electron microscopy, where we can obtain even in normal routinely microscopes, conventional electron microscope like the one which I have shown you in the beginning of this course. It is possible to achieve different other kinds of information like Z contrast, the atomic number contrast information, or even you can actually take high resolution images using these the stem features to obtain or to see the heavy atoms present in a particular material, which these are all discussions we will do in the next class.